Imagine a robotic arm reaching out to catch a falling plate. If the system's its predictive world model takes 3 seconds to simulate the optimal trajectory, well, that plate is already shattered on the floor.
The latency totally renders the intelligence useless.
Exactly. We are jumping straight into a brand new paper from MIT and Harvard today that attacks this exact problem called DriftWorld, fast world modeling through drifting.
Yeah, and for the AI researchers and machine learning engineers listening, here's the core thesis right up front. Predictive world models are absolutely indispensable for robot planning, right? Because they let a system imagine the physical outcome of its actions before committing to them in the real world.
Right.
But our current state-of-the-art models rely overwhelmingly on diffusion. And diffusion architectures are fundamentally bottlenecked by their multi-step denoising process.
You can't perform real-time action search when generating a single future frame requires, dozens of iterative network passes.
Exactly. DriftWorld solves this by replacing diffusion entirely with a drifting generative model. It learns an action-conditioned drift during the training phase, allowing it to generate high-quality future video frames from a current observation and an action sequence in a single forward pass.
And the performance metrics on this architecture completely altered the landscape for deployment. I mean, it runs at over 30 frames per second.
Which is incredibly fast.
Yeah. That equates to a 17x speed up over current diffusion baselines on standard, really complex robotic benchmarks like Bridge V2 and RT1. And it does this while sustaining or even surpassing the visual fidelity of those much slower models. So welcome to AI paper slop.
It's a massive jump. But to appreciate why the authors had to build DriftWorld in the first place, we kind of have to dissect the exact mathematical bottleneck trapping current systems.
Right, the root of the problem.
Exactly. We need to look specifically at a framework called Generative Predictive Control, or GPC.
So let's visualize how GPC operates in a physical environment. Like if a robot is tasked with picking up a fragile mug, the control policy doesn't just execute the very first movement it calculates.
No, not at all.
Under GPC, the policy proposes a whole batch of candidate actions. It might generate, say, 50 different potential joint trajectories for the robotic arm.
Right. And then the robot uses its world model to simulate the future for all 50 of those options. It basically rolls them out in its imagination to predict the visual and physical consequences of every single trajectory.
And then a reward model evaluates those hallucinated futures, scores them based on which one safely grasps the mug, and the robot finally executes a winning action.
But the fundamental constraint emerges when you rely on a diffusion model to generate those 50 futures, because diffusion is a Markov chain.
Right. Stepping backward from pure Gaussian noise to a clean image over 20, 50, maybe even 100 discrete steps.
Yeah, because of that, those imagination rollouts end up consuming like 90 to 95% of the total computation time. We are typing 3 or more seconds per decision cycle.
Which is wild. In the software domain, a 3-second delay is just a loading spinner on a web page. But in the robotics domain...
Catastrophic.
Yeah, a 3-second delay means the physical environment has permanently changed. The plate has slipped, the target object has rolled away, or, a human has entered the workspace. The physics of the real world make that latency a complete non-starter for closed-loop control.
It just doesn't work.
Using a diffusion model for real-time robot control it's like hiring a classical oil painter to give you real-time traffic updates.
That is a perfect analogy.
The rendering is gorgeous, the lighting is physically accurate, the detail is immaculate, but by the time they finish the canvas, you've already missed your exit.
Yeah.
You cannot wait for the paint to dry when the world is moving.
You really can't. So the underlying architecture has to change fundamentally to shift from those oil painting speeds to live feed speeds. Which brings us to the actual mechanics of drifting generative models and how they achieve that single-step mapping from pure noise to structured video data.
So how does drifting actually circumvent that multi-step process? Because we're still trying to map a random noise prior to a highly complex video distribution.
Right.
If the network isn't taking 50 sequential steps to gradually denoise the image, what is actually happening mathematically in that single pass?
Well, drifting shifts the computational burden entirely to the training phase.
Oh, interesting.
Yeah, instead of step-by-step denoising during inference, drifting defines a continuous vector field. The authors call it the drifting field. During training, this field governs how the model's generated samples, which we call the push-forward distribution, how they must evolve to reach the true data distribution.
So by the time you deploy the model for inference, the network simply evaluates that field once.
Exactly. Just one pass.
I want to make sure I have the correct mental model for this training loss, though. You pass a noise vector through the network once, generating a completely garbage video chunk.
Yep, total static.
And the drifting field calculates a vector that basically acts as a directional compass in this high-dimensional space, telling that garbage sample exactly which direction to move to become a realistic video frame.
That's right. And that directional compass is calculated through a contrastive loss mechanism.
Okay, break that down for me.
The drifting field computes a mean shift vector that exerts two simultaneous opposing forces. First, there's an attractive force pulling the generated sample toward a positive sample. In this context, the positive sample is the ground truth future frames from the dataset.
Got it.
But simultaneously, there is a repulsive force pushing the generated sample away from negative samples, which are just the other future frames the model itself just generated.
It operates a lot like fixed-point iteration, then. You're shifting the model's prediction toward a frozen target that is offset by this drifting field.
Yes.
But there is a crucial nuance here for action-conditioned video that differs from standard generative AI. If you're training an image generator to create a picture of a dog, you have thousands of positive samples.
Oh, absolutely.
There are countless valid ways to draw a dog. But DriftWorld doesn't have that luxury.
No, it doesn't. The constraints of physics dictate a much stricter reality here. For a specific history of visual observations and a specific commanded action sequence, there is only one true outcome in the dataset.
Because physics is deterministic in that short window.
Right. If the command is to move the robot arm 5 centimeters to the left, the positive sample is the single video where the arm actually moved 5 centimeters to the left. DriftWorld uses exactly one positive sample for its attractive force.
Wow. So the model is fiercely constrained by the action vector, yet it still utilizes a massive cloud of negative samples. The architecture uses 64 negative samples per forward pass to create that repulsive field and sculpt the distribution boundaries.
Yeah, 64 is a heavy load.
So when you deploy this on a physical robot, Inference is literally concatenating the noise, the visual observation, and the action sequence and running one single forward pass. Bam. You are operating at 30 frames per second.
Bam is right. But, applying a vanilla drifting model to robotic data will fail catastrophically without heavy modifications.
Of course, it's never that easy.
No, the researchers had to engineer 3 distinct architectural adaptations to tailor this mathematical concept for complex physical environments.
This is where I start wondering about the reality of messy datasets. If you take a dataset like Bridge v2, which is full of messy kitchens, complex backgrounds, shifting lighting.
It's a nightmare for models.
Yeah. Won't a single-step model just optimize for the easiest path to a low error? Like, it could predict the static background perfectly, minimize the majority of the pixel loss, and just ignore the action vector entirely, leaving the robot gripper frozen in place.
The network will absolutely take that lazy route if you do not constrain the loss function.
Yeah.
I mean, the vast majority of the pixels in a kitchen scene remain identical from frame to frame.
Right.
To counteract this, the authors introduced motion weighting. They calculate the feature differences between the current frame and the future frame. Any spatial location exhibiting significant motion receives a massively magnified weight in the drifting loss.
So you force the network to care disproportionately about the pixels that are actually moving, like the gripper and the object it is interacting with.
Exactly. And they also modified the negative sample distribution to penalize inaction even further.
How so?
Alongside the model's generated frames, they injected real, ground truth, no action frames into the negative sample pool. These are actual frames from the dataset where the robot is demonstrably sitting still.
Oh, that's brilliant. So the repulsive force of the drifting field actively pushes the generated output away from being static.
Exactly.
If the policy commands an action and the model attempts to predict a static gripper to save computational effort, it gets heavily penalized because it basically resembles the no-action negative samples. It is an ingenious way to mathematically punish the lazy background prediction.
It really is.
Yeah.
But motion weighting alone introduces another severe challenge.
What's that?
Well, if you amplify the loss on moving pixels and compute that contrastive drifting loss in raw pixel space, you run straight into the classic mean-squared error blurring problem.
Right, because the model is uncertain about the exact future pixel values of a fast-moving object, so it just averages the possibilities together.
Yes, the result is a blurry smudge right where the gripper should be.
Which renders the prediction completely useless for fine motor control. The robot can't determine the orientation of a blurry smudge, so it can't plan its next move.
Exactly. This necessitates the second adaptation, which is feature space drifting. Instead of computing the mean shift vectors using raw RGB pixels, the researchers project both the generated outputs and the ground truth targets into a dense semantic feature space before calculating the loss.
Okay, and they specifically employ pre-trained vision transformers for that, right? Relying on Dynov 2 or Dynov 3.
They do.
The logic there being that the kernel used to calculate the mean shift vectors relies on pairwise similarity. If you calculate similarity in a space that encodes deep semantic meaning like understanding the structural difference between a metallic gripper and a wooden block, the distance metric forces the model to generate structurally coherent objects rather than just matching color values pixel by pixel.
Spot on.
Yeah.
The network learns to preserve the sharp structural integrity of the objects in motion. But for anyone designing an inference pipeline, there is a highly vital detail to remember regarding this step. DNO is utilized exclusively during training to compute the loss.
Oh, wow. So the massive vision transformer never even touches the inference loop.
Never.
Once the unit learns the mapping to that semantic space, DNO is completely removed from the pipeline, preserving those sub-second inference speeds.
Right. Which leads us to the third adaptation, the actual UNet architecture itself. They couldn't just use a standard video generation backbone.
Because standard models don't care enough about exact timing.
Exactly. They had to ensure tight temporal adherence to the commanded actions. A standard video generation model might just globally condition an entire generated sequence on a single block of text or a single prompt.
But for real-time physical control, action at time and note must precisely dictate the visual transition to frame +1.
Yes. So they solved this by integrating feature-wise linear modulation, or film, to condition the network on a strict frame-by-frame basis.
So the action vector for a specific time step dynamically modulates the affine transformations within the neural network's feature maps for that specific frame generation.
You've got it. And they combine this frame-wise film conditioning with factorized spatial temporal convolutions.
Factored convolutions, right. Standard 3D convolutions are computationally exorbitant, and they often blend spatial and temporal info in ways that blur fast motion.
Right. So by factorizing them, applying 2D spatial convolutions followed sequentially by 1D temporal convolutions, the network maintains really crisp spatial details while enforcing strict temporal consistency across the frames.
The combination of film and factorized convolutions basically ensures the robot's generated trajectory physically obeys the sequence of actions second by second.
It does.
The architectural math is incredibly elegant, and the solutions for visual fidelity are so clever. But the ultimate test for machine learning engineers listening is whether this actually improves physical execution. When they hooked DriftWorld up to a control policy, what did the performance benchmarks look like?
The evaluation was comprehensive. It spanned several demanding datasets, including push-T, RoboMimic, Bridge V2, RT1, and language table. Visually, DriftWorld matched or surpassed diffusion models.
That's impressive on its own.
Yeah, and instead of just relying on pixel-perfect accuracy metrics like PSNR, the researchers also evaluated metrics that capture how humans and systems perceive structural quality and temporal consistency, stuff like LPIPS, FID, and FED.
So it beats diffusion not just in raw numerical error, but in generating a cohesive, physically plausible video that a robot can actually use.
Exactly. The true crucible for this model, however, is the GPC rank experiment for online policy improvement. Push-T is that classic benchmark task where a robotic arm tries to sweep a T-shaped block onto a designated T-shaped target.
Right. So how did the experimental setup work?
They used a base diffusion policy that samples 50 potential actions. DriftWorld rolls all 50 candidates out in its imagination, generating the visual future for each potential movement.
And then a reward model evaluates those 50 futures and selects the one where the block is closest to the target.
Yep. Using DriftWorld as the simulation engine boosted the base policy's success rate, measured by intersection over union, from a baseline of 0.635 up to 0.781.
That is a tremendous capability jump, purely from granting the robot the ability to mentally simulate its options before moving. But the latency is the truly transformative metric here, isn't it?
Absolutely. Simulating those 50 parallel action rollouts with DriftWorld took only 0.912 seconds.
Less than a second.
Now compare that to running the exact same GPC rank pipeline using AVDC, which is a state-of-the-art diffusion-based world model. Generating those same 50 rollouts with AVDC consumed over 106 seconds.
0.9 seconds versus 106 seconds. Returning to the real world, a 106-second delay means the environment is completely devolved.
Right.
A human walked past the robot, the lighting shifted, and the object slid on the table. AVDC is practically useless for closed-loop control. DriftWorld's sub-second latency is what finally drags generative predictive control out of theoretical papers and into physical viability.
It really does. Online control is a massive breakthrough, but researchers also urgently need these world models for offline simulation.
Right, because deploying an experimental, unproven policy on a $100,000 physical robot arm is highly risky and computationally expensive.
You don't want it thrashing around, destroying the last.
Exactly. You need a software simulator accurate enough to act as a reliable proxy. You want to feed the model a new policy and ask, if I deploy this software on the real hardware, will it perform the task or will it just shatter the plate?
And DriftWorld apparently excels here too. When they plotted the predicted success rate of policies in DriftWorld against ground truth physics simulators, the Pearson correlation coefficients were stellar.
Just how stellar?
We're talking 0.9515 on push-T and 0.9916 on the Robotic lift task. It perfectly distinguished the robust policies from the dangerous ones.
But wait, achieving that level of accuracy must have been tough because, well, datasets like Robotic are predominantly composed of successful human teleoperation demonstrations, right?
They are.
So the model is overwhelmingly trained on videos where the task goes perfectly right. If the model only knows success, you run headfirst into a massive confirmation bias problem.
Oh, absolutely.
If a bad policy feeds it a terrible action vector, say, commanding the gripper to close 3 inches away from the block, won't the world model just hallucinate a success? Its physics engine has never seen a failure, so I'd imagine it magically fixes the mistake in the video and shows the block being lifted anyway.
That is exactly what happens. The model suffers from exactly that kind of utopian confirmation bias. The authors discovered their initial model was providing dangerously optimistic estimates for bad policies.
It just assumed everything would work out.
Right. It imagined the block floating into the air even when the gripper missed entirely. To rectify this hallucination, they had to explicitly teach the AI how to fail.
Ah, so they deliberately post-trained DriftWorld on a data set of failure demonstrations.
They did, gathering videos from early incompetent policy checkpoints where the robot drops the object, misses the target, or just moves erratically.
By exposing the drifting field to these failures, the world model learned the causal physics of error. If you close the gripper on empty space, you get empty space.
Right. It underscores a critical principle for anyone building these systems. A world model is not just generating pretty pixels. It is regressing the causal physics of the environment.
If your dataset lacks negative physical consequences, your vector field cannot mathematically map a bad action to a realistic failure state.
Exactly. Yeah. Now, DriftWorld represents an undeniable leap forward for world modeling, but for the engineers listening who are considering integrating this architecture into their own stack, we have to examine the trade-offs.
Right, there's always a trade-off. You do not get a 17x speedup without paying a toll somewhere in the pipeline.
The toll is paid heavily in VRAM during the training phase.
Because of the negative samples.
Exactly. Recall the contrastive drifting loss. It demands the calculation of the repulsive force from those negative samples. The paper utilizes up to 64 negative samples per forward pass during training.
Think about the hardware constraints for that process. It is like trying to hold 64 completely different parallel universes in your GPU short-term memory at the exact same time.
It's massive.
You are storing the activations for 64 generated video chunks, plus the ground truth, and computing the massive dyno feature projections for all of them simultaneously for a single batch item.
The VRAM appetite is staggering. This hard caps the number of context frames you can input and the number of future frames you can generate in a single training chunk.
Which means it can bottleneck the long-range temporal consistency of the model when compared to autoregressive diffusion models.
Right, because diffusion models can train on much longer sequences since they require significantly less memory per frame.
So you are fundamentally trading inference latency for training complexity and memory overhead. But in the robotics domain, that is a highly advantageous trade.
It's the trade you have to make.
You have access to massive server farms to absorb the training cost, but you are severely restricted to a small, low-power onboard compute unit for real-time inference on the physical robot.
Exactly. And the authors do propose future mitigations, suggesting the use of sparse observation histories or advanced video VAEs with higher temporal compression to squeeze longer sequences into the VRAM budget.
Right. Regardless of the current memory constraints, the core paradigm shift is totally validated. Drifting successfully circumvents the multi-step sampling bottleneck that has crippled generative predictive control for years.
It's a huge win for the field.
Which leaves you with a final, broader implication to consider for your next architecture design. If this drifting paradigm can achieve 17x speedups and 30-plus frames per second for high-fidelity action-conditioned world models by entirely abandoning multi-step diffusion.
What happens when it scales?
Exactly. What happens when this scales? We are constantly amazed by the visual fidelity of massive generative video models like Sora, but they take minutes to render a few seconds of footage.
Yeah, they're beautiful, but so slow.
Could single-step drifting be the architecture that finally bridges the chasm between generative video models and real-time, playable physics engines for video games?
Oh, that's a wild thought.
Imagine a completely hallucinated virtual world with photorealistic fidelity that reacts to your controller inputs in under 16 milliseconds. The latency barrier is breaking. Think about that for your next project.